In this video here, we're going to take a look at acceleration varying with time. Now, we can use calculus for a particle moving in a straight line with acceleration that varies with time. So let's just begin here then by recalling some key results linking displacement, velocity, and acceleration by using calculus. So for the first point here then, to find the velocity, if we're given the displacement here, all we need to do then is just differentiate with respect to time. And for the second point here, to find the acceleration from the velocity, again, all we need to do here is just differentiate with respect to time. So hopefully you do recognize these first 2 points here. If you don't, I'm not really too sure how you've made it this far into further mechanics, given that this is pretty basic stuff and it's something that we learn in A-Level Maths. But either way, well done. And the way that we express this here then mathematically is by the following relationship. So V here, the velocity, is equal to dx by dt. And then for the acceleration, A here is equal to dv by dt, which we can also express then as the following. So this is just the same then as the second derivative here of the displacement x, again, with respect to time t. And in a similar fashion here, we can now go backwards. So if we want to obtain the velocity and we have the acceleration, what we need to do here then is just integrate with respect to time. And for the second point here then, to obtain the displacement from the velocity, all we do here, again, is just integrate with respect to time. And mathematically then, this will look like the following. So this here is our relationship then for integration. And this is how we link displacement, velocity, and acceleration if we're going backwards, right? So the velocity v here is equal to the integral then of the acceleration a here with respect to time t. And then for the displacement x here, well, that is equal to the integral of the velocity v here, again, integrating with respect to time t. Now, if you have watched any of our previous, so we did this particularly in A-Level Maths, right? So if you've watched our applied videos here for A-Level Maths, what we did then is I cover this as x, v, a, and I cover this moving down in a straight line here. So if we have the displacement x here, and we want the velocity, or if we're given the velocity, and we want the acceleration, the way that we go down here then is by differentiating with respect to time t, so d by dt. And then if we want to go the other way, right, so we want to go up now, so if we have the acceleration and we want the velocity, or if we have the velocity and we want the displacement, we're going up here. The way that we deal with that here then is by integrating with respect to time t. Okay, the arrow there is that bad. I'm going to redo it. It's a little bit of a pedantic point, but we like things to look somewhat neat here. There we go. It's still not perfect, but it'll do, right? So for example then, if you have the displacement and we want the velocity, we would just differentiate the displacement here with respect to time t, and that would give us the velocity, as we've just seen here, right? Same again for the acceleration, that is dv by dt. If you want the velocity and you're given the acceleration, well, all we do here is integrate the acceleration with respect to time t. Now, all of these relationships here should be pretty standard stuff. And these are things that you should be very much familiar with by now, right? We are studying further mechanics too. Like I said before, if you've made it to this point here and you don't recognize these relationships, I'm not really sure how you've made it to this point, but either way, well done. Somewhat of a massive accomplishment. But there we go, right? So that concludes this introduction here to acceleration varying with time. So a lot of this is just largely A-Level Maths material, right? It's more of a recap than anything. But as always, right, let's just work through a practice question together. So let's not waste any more time then, and let's just get started with this practice question. All right, so let's just get started then with the one practice question here for acceleration varying with time. So what do we have then for this question here? Well, as we can see then, what we've got here is a particle P that is moving along the x-axis, and at time t equals 0, the particle is at the origin O, and is moving with speed 3 meters per second in the direction OX. Now, at time t seconds, where t is greater than or equal to 0, the acceleration of p is given as the following here. So 2e to the power then of minus 0.5t meters per second squared, directed away from O. And as we can see then, we've got these 3 different parts here for this question. So let's just begin then with part A here. So for part A then, what we want to do here is just find the velocity of p at time t seconds. So to begin with here then, what we're given is the acceleration of p, right? That is 2e to the minus 0.5t meters per second squared. So let's just make a quick note here that A the acceleration here is the following. So it is 2e to the minus 0.5t. Obviously, if you don't forget the units here, that is meters per second squared, just like that. Now, to begin with here then, we want the velocity of p at time t seconds, right? So what I'll do here is just let the velocity of p at time t seconds be v meters per second, right? In that case then, we know that v here, the velocity, is equal to the integral then of the acceleration a here with respect to time t, so dt there, just like that. So let's just replace a here with this expression. So that then is the integral here of the following. So 2e minus 0.5t, just like that, integrating here with respect to t. Perfect, right? And hopefully this integral here is nice and straightforward. 2 divided by minus 0.5 here would just give us minus 4. So the result here then is minus 4e to the minus 0.5t. That doesn't change, right? And just notice here then, we do not have any limits on our integral. So don't forget then your constant of integration. So plus c, right? Now, obviously, I can find the value of c here because I do know some initial conditions here. We know then that when t is equal to 0, the particle is at the origin O and is moving with a speed here of 3 meters per second. Let's just make a quick note here. When t is equal to 0, then the speed here, v, is equal to 3 meters per second, right? So v is equal to 3. So what we're going to do here then is just substitute these initial conditions into this expression here. This was for v, by the way. So v here is equal to the following. So in that case then, 3 here is equal to, so it is minus 4e. This is minus 0.5 times t, which is just 0, right? So minus 0.5 times 0 is just 0. So minus 4e to the 0 plus c. Okay? Well, obviously, anything to the power of 0 is just 1. So minus 4 times 1 is minus 4. So what I've got here is c minus 4 is equal to 3. And therefore, then, c here is equal to 7. Perfect. Okay? So in that case, then, going back to v here, let's just take this all the way down here. We can see then that v here is equal to, so it's minus 4e to the power then of minus 0.5t plus c, where c is 7 here. An alternative way to denote this here, and it is a slightly nice way to do this then, is to put c first, given that that is positive, right? So what I get here then is 7 minus here 4e minus 0.5t, just like that, okay? And there we go. So this here then gives us the solution to part A. Perfect, okay? So let's just continue then with part B here, over to the left-hand side. So for part B then, what we want to do here is just show that the speed of p cannot exceed, English is hard, cannot exceed 7 meters per second. Right, so hopefully this isn't too challenging, right? To answer part B here, let's just think about how the exponential function actually behaves, right? So we know then that for all x here, for all x here, you should be aware then that e to the x is strictly greater than 0, right? So e to the x here is strictly greater than 0. So in that case then, for all t here, so let's just kind of write this down here. And so for all t then, what we can say here is that for e, the minus 0.5t here must also be strictly greater than 0, right? So this here is strictly greater than 0. And in that case, then it does follow that this result here for v, so 7 minus 4e to minus 0.5t, must be strictly less than 7, right? So it follows then, that v here, which is this expression, so 7 minus 4e to minus 0.5t must be strictly less than 7, right? Because no matter what, it doesn't matter how small this is, this here will be positive, right? So no matter what then, we're always subtracting something from 7. It doesn't matter how small that is, we're always taking something away from 7. So no matter what, it will always be strictly less than 7, right? So therefore the speed of P cannot exceed 7 meters per second. Perfect. Okay. And there we go then. So that gives us the solution to part B. And then finally, to finish with here, we have part C, right? So for part C then, to finish with here, all we want to do is just sketch a velocity time graph to illustrate the motion of P. So it's time to demonstrate my amazing art skills. So let's just quickly start then with the axes here. And by the way, it's just a sketch. It doesn't need to be perfect, right? So this here will be my vertical axis, something like that. It's not too bad. It is supposed to be a straight line, but it'll do. I'm doing this freehand. And then I've got the horizontal axis as well. Again, this should be a straight line. As you can see, it's not the easiest, but it'll do, right? So let's just label the axes here. So the horizontal axis here is for the time t, right? So it's for the time t here in seconds. And then the vertical axis here is for the speed, right? So v meters per second. So v meters per second. And basically, all we want to do here is just sketch this function here, right? 7 minus 4e minus 0.5t. So in terms of sketching this here, to begin with, let's just kind of mark down where it will cut through on the vertical axis here for the speed, right? Which we know then, based on this initial condition here, is 3. If that wasn't given to you, but you did have this function here, right? I would just let t be equal to 0. So 7 minus 4 times 1 here. So 7 minus 4 is just 3. As we're told here anyway, right? So you should obviously get the same either way. So if I just mark 3 as here, for example, it's not perfect, but it will do. Let's just say that that is 3. And then in terms of the general shape here, it's going to be kind of like, if I just draw a quick sketch, it's going to look, say, something like that, okay? Kind of curving upwards here. And because we know then that the speed of P cannot exceed 7 meters per second here, we're essentially going to have an upper bound in terms of the graph here. So if I just mark 7, so let's just say there roughly, okay, then I know that as the time t increases here, then it's just going to kind of go like this, okay, kind of going up and up and up. Obviously, this 7 here, if I just mark it then in a different color, this 7 here is supposed to be an asymptote. My graph, as you can see, isn't perfect. So let me just quickly redo that because that's not very good. What I'll do here is I'll just mark the asymptote first, and then I'll draw the graph. It's a little bit easier to do it like that. So this 7 here is an asymptote, right? Because the curve will approach the line v equals 7, but it will never touch it. Okay, so going back to my original pen color here, let's try again. In fact, it might be a little bit easier if I just draw 3 a little bit further down. So let's just try a little bit further down here. Let's just say here, obviously this coordinate axis here isn't clearly to scale. It's not brilliant, but it'll do. So we start at 3 and we kind of curve upwards like this. So something like this here would be absolutely fine, okay? It's got the general kind of shape here that we want. It starts at 3 here on the vertical axis. That is absolutely perfect, right? As we said then, it will never actually touch the line v equals 7 here because it is an asymptote, right? The actual velocity here of 7 meters per second is what we call the terminal or limiting velocity of t in this context, right? But there we go then. So as you can see then, this gives us the solution to part C. This here was the solution to part B. And this here was the solution to part A, giving us a solution then to the one practice question for this video here. And that brings us to the end then of this video here on acceleration varying with time.